Hi everyone, this is Xiaofu, a research scientist whose background is in dynamics, vibration, and control. Let's continue my YouTube channel and this lecture for this control topic, design a control system from scratch. On this current lecture, we will continue what we have left from the previous one. So the topic of this lecture will be linearization of MIMO system, especially on how you linearize this system step by step and use that correct approach to linearize it. And in the next lecture or next video, we are going to focus on how you can deduce system properties from state space representations. Okay, from what we have left last time, let's have a quick recap. So last time we have mentioned multi-input, multi-output static nonlinearities. So when I mention static, that means you don't have dynamical state variables over here. So you don't have active states x over here in your system. So that's why your function y, which can be considered as output function y, is only a function of input u, not a function of state variable x. So that's why you say y1 is a function of u. So here, when you are doing the linearization, you have to make sure your delta y is small enough. Otherwise, your linearization won't be valid because a nonlinear system, if you are linearized with respect to an interest of point, if you are getting far away from your interest of point, then your linearization or local slope will also be invalid. So that's one very important concept we have to memorize. So then let's use an example. As we mentioned, this static nonlinearity, you don't have dynamic variables x over here. So as you can see, your function f is only a function of input u, where you have two different inputs, right? So what you can do, linearize it, so you have to find out what is your function f partial derivative with respect to each input, individual inputs u, u1 and u2. If we go back, you can see that, right? If you have multiple inputs, you have to find each partial derivative with respect to f1. So right now you don't have u1 and u2, so you find partial derivative of f with respect to u1, you get 3u1 squared u2 plus 4u1 plus 1, right? If you try to find the function of f with respect to the partial derivative of u2, so you get u1 cubed plus 15u2 squared, and as the linearization point we've already defined, which is 2 and 1 for u1 0 and u2 0, we plug it in and get this linearization function with respect to this u1 0 and u2 0. And if we use another example, which we previously was looking at multi-in single output static nonlinearity, right now let's have multiple output as well. So we have not only y1, we also have y2, right? y1 equals to the first function, y2 equals the second function. We also have a sine function, but that's fine. Let's start with y1. So if we start with y1, we are trying to derive function f1 or y1, function y1 or f1 with respect to u1 and also with respect to u2 with respect to all the individual inputs. If you have three inputs, then you will have to have another one, the partial derivative with respect to u3, since you only have two, right? So then, as you can see, if you do f1 partial derivative with respect to u1, you get 3u1 squared u2 plus 4u1 plus 1. And the other one also not that difficult, but since the first one is simpler, you don't have this sine function. With respect to u2, you have u1 cubed plus, okay, this is u1, so with respect to u2 it will be 0. This is also 0. Then you will have 15 u2 squared. The other one is you have the sine function. What you can consider is this sine function is always a constant, right? So it's almost always a constant. So if you look at f2 with respect to u2, so let's say u1 cube 0, 2u1 squared 0. This is absolute value of u2. So, but since our point of interest is larger than 0, so you can consider this as u2 times u1, right? So which means you get the if you do the partial derivative with respect to u2 for f2, then you get u1. And this is a sine function. You always get a constant output, so it doesn't really depend on your u1 and u2. So then that will be 0 again. So looking at everything here is just for static nonlinearities, though it's multi-in, multi-output, but it's still not complex enough. So since a lot of static system, we have it over here. Let's say static system, you might have, let's say, Ohm's law, let's say your voltage and current resistor are kind of in a linear relationship. But that can also sometimes be nonlinear if, let's say, your resistor can be, let's say, a time or temperature dependent, right? So, but whichever one you use or you consider, this linearization for a static nonlinearity is always a gain over here, right? So if you look at a nonlinear dynamical system, that will have states over here. So dynamic means you have state variables that is not only depends on there's not only a simple relation, it might depend on different time, current state, previous inputs, so all will be combined together. That's why that will be more complex than a static system. So if you consider a dynamical system, so you have x dot equals to ax plus bu, which we have already seen that from the state space representation. But still, you have to make sure linearization always that has to be small enough with respect to your point of interest. Otherwise, this linearization won't be valid. So let's say you have multiple ways to derive your linearization. I would say the first way you have to do is, or the standard way is, you have to derive the state space representation. So that will be the most simple way that you can start with. Let's say your A matrix generally depends on how many state variables you have. If you have X state variable, you have n by n A. For B matrix, it depends on the state variable and also meaning your I would say your state variable. Sorry, meaning it depends on the number of your inputs for each individual function y or f. So your function y, the output function y is equal to c times x plus du. So C matrix also depends on how many outputs are you supposed to have, right? So if you have only a single input, if you have a single output, your C matrix will be 1 by n times n by n. Your C matrix can be 1 by n times your n by 1 state variable, so you have a single output. Let's take a look at a more interesting example instead of only looking at the mathematical concept. But before we move on to the example, so one last thing I'm going to mention is for the MIMO nonlinear dynamical system, linearization, step 1, you have to find your state space representation. And after that, you will take the partial derivative of your function f, which your f is defined here, x dot equals to f, which is a function of state variable and also input u. Y is the same thing. Y can be c times x plus du. So it's a function of state variable and also input u, right? So after knowing that, so your A matrix can be directly derived from state space representation, or you can use this partial derivative of your f with respect to x, right? So whichever way you choose, you will end up with the same thing. I will use example to explain how you can eventually get the same thing. Okay, here I want to jump a bit to let you understand what is the best way, or what is the right point you should to pick for linearization for a nonlinear dynamical system. So we'll always have to linearize about an equilibrium point, which is the one that I mentioned here, right? So, but why linearization about the equilibrium point? Because with respect to linearization to find with respect to the equilibrium point, it is time invariant. So if your x dot is not equals to 0, it will have a time varying system. So A, B, C, D are also time varying. So that's why we need to linearize about this equilibrium point where your x dot equals to 0. Okay, so here is the correct process which you should use for linearizing a nonlinear dynamical system, which can be expressed by x dot equals to f, x as x of u, and y equals g of x and u. So derive firstly the state space representation, find your linearization with respect to the equilibrium point. This equilibrium point, as we mentioned, it gives you the time invariant system. And then derive A, B, C, D accordingly to finalize the formula. Okay, let's use a mass spring damper system whose damping is a nonlinear term, where your damping here is a function of y dot cube. So let's find the state space representation, which has to be represented by multiple first order differential equations, right? Which we have discussed that in the previous lectures. So x1 dot equals to x2, then that's your function f1, f of u, right? Then x2 dot equals to, which is the y double dot, equals to rest of the term that as we expressed here. So that is f2 x of u, right? So then let's find your equilibrium point. As we've already defined in this example, your u0 is 1, which is the interest of point. So if you find x1 dot equals to 0, you also derive your x2 equals to 0. If your x2 equals to 0, then from the rest of them, you will find your x1, 0 will equals to u over k. So here we get state space representation and also your equilibrium point. Let's find ABCD matrix. So ABCD matrix, you can use a simple way, as you already know x dot equals to ax plus bu, right? So look at your state space representation here. Your x1 dot equals to 0 times x1 plus 1 times x2, right? So that's why your a can be 0 and 1 right here. And similarly, x2 dot equals to 1 over n minus times minus x1. So here you will see that, okay, so but your x1, 0 equals to u over k, right? So if you multiply them together, you get minus k over n. So similarly, you can get the last element of a matrix. Or you can look at your f1. What is your f1, right? Your x dot equals to x1 dot equals to f1, x2 dot equals to f2, right? Your f1 is indeed just x2, right? Then x2, which is take the partial derivative with respect to x1, is 0. With respect to x2 is 1, right? So similarly, you have f2 equals to everything here written. So let's check your f2 partial derivative with respect to x1, what it will be, right? So if you look at it, it will be just minus k, since that's the only term have x1 over here. So minus k times, or divided by n. So that's it, right? So you can find it very easily. So I would say whichever way you use to derive A, B, C, D, you will end up with the same thing, but just depends on your own preference. And another example, which is let's say a pendulum system, where the input is the moment applied at the pivot, which is the pivot point M, and the output is the theta, right? Output is a theta. So you have to derive a linearized state space representation around the equilibrium point corresponding to M equals to M0. So here, let's find the state space representation. That will start with doing the equation of motion first, right? So as we generally have for, let's say, rotational system, not a linear motion, for rotational dynamics, it will be J times alpha, which alpha is theta double dot, equals to the summation of all the moments. So similarly, you also have m, which is a mass, times a, which is the acceleration that can be expressed by m times x double dot. This is used for let's say for linear system. Sorry, not linear system. This is used for linear motion. So equals to the summation of all the external force, right? External force. So similarly, we are using the summation of the moments because this is the rotational motion. That's very simple and easy, where you get m subtract by mgl times the sine theta, right? So here, you know the equation of motion already. You have to translate it to two different first order differential equation, where your x1 dot equals to x2 and x2 dot equals to 1 over ml square times the bracket m, which is the moment applied as a pivot point, subtract by mgl times sine theta. But theta is actually your x1 here. So let's find your equilibrium point. You make all your x dot equal to 0. Let's say x1 dot equals to 0, you get x2 equals to 0, right? And if you have your x2 equals to 0, what you can derive is you have this function over there. So then you get sine x1 0 equals to m over mgl, right? But since then you will have to know, okay, what is my theta x1 0, right? So you take the arc sine to get your theta over there. So right now, let you find the equilibrium point. Let's derive your ABCD. Let's use the mathematical expression. A matrix is equals to PD partial derivative of your f1 with respect to all the state variables. For this one, you have x1 and x2. You also have two first order differential equations. So in total, you have a 2 by 2 A matrix. So then A matrix, what is your f1? Your f1 is equals to x2, right? So then with respect to x1, the partial derivative is 0. And with respect to x2, you get 1. So f2, this is f2. This is your f2. So similarly, if you take the derivative of your x2 with respect to x1, you get cosine, right? Sine, if you take the derivative, you get cosine. But since it's only a function of x1, if you take the derivative with respect to x2, it is 0. So similarly, you do the partial derivative for f with respect to m. As m is your input, right? You will have a single input. If you look at it, the first term you don't even have m. The second term you have it. So second term you only have your m over here. So that's why your second term for b is 1 over ml squared, right? So similarly, you can derive that for your same matrix. Your g is c times x plus du, right? So what is your G, right? G, as you want to have your output is the theta, right? So that means your output Y is a function of theta. So that means your C matrix will be 1, 0, and you don't have D matrix over there, as your output, as we mentioned, is only theta. So right now you derive all A, B, C, D matrix, and then you linearize that already with respect to your equilibrium point based on your state space representation. So then you can write down your final formula for your linearization equation. That's it. That's everything for this lecture. If you like my YouTube channel, please subscribe to my YouTube channel. That will motivate me a lot to make more videos. Thank you.